Let's get started. Okay, so today's topic is on BI. It's on Apache Superset, right? Query engine must-haves for the best Apache Superset experience, right? Hello, everyone. I am Sida Shen. I am a product manager at CelerData, and I'm also a StarRocks contributor. Okay, so let's get started. So first, let's take a look at the agenda. First, we're going to talk about what is Apache Superset and what it does, a little bit of the history, and why do people love it, right? And then we're going to talk about the pain points. We see in the StarRocks community that the pain points that our user used to face, with Apache Iceberg, right? And then we're going to talk about the requirements for the underlying engine that powers Apache Superset, the requirements that to take fully advantage of the advantages of, why Superset is good, right? And then we're going to talk about the technologies that enable interactive analytics, and then we're going to show a demo. Okay, let's get started. So first, Apache Superset, right? Apache Superset was built in Airbnb as a hackathon project, open source in 2016, and it's been Apache project since May of 2017, right? Well, it's a BI tool. It's has a beautiful GUI, right? And it's really known, to do interactive analytics, right, with low latency, and you can build your dashboard with no code, right? And it's a very thin layer, right? It's basically a GUI with a SQL generator, right? It generates SQL and send it to the underlying engine to process. So it's a very thin and lightweight kind of application on top of your data architecture, right? So it leverages the power of the existing data architecture without actually needing to ingest your data into another system, right? Also has one of the biggest open source BI community in the world in our field right now. Have just insane number of stars, and over 14,000 people in their Slack channel, right? And by talking with a lot of Apache Superset users, specifically in our StarRocks community, right, we spot two main challenges that people see with Apache Superset, right? So first is a lot of running dashboards, right? They're battling with slow and, more importantly, unpredictable query performance, right? And then the complex architecture, right? Users are normally they're maintaining a completely separate data warehouse, proprietary data warehouse, purely to serve Apache Superset, right? To serve interactive queries, they need a proprietary data warehouse to get that kind of performance, right? And although they have the performance, but the complexity, the overhead of actually maintaining that infrastructure is a big pain. We see a lot for the users in the StarRocks community, right? And there are some requirements too, specifically for running BI with Apache Superset, right? Requirements for the underlying engine. So first is slice and dice analytics, right? That requires, you look at many different metrics and interactively, right? So your engine needs to deal with on the fly queries really fast, right? So you want to do those computations on the fly, right? On very complex SQLs with a lot of joins, a massive amount of data, and with aggregations, sometimes very high cardinality aggregations, right? Really a challenge for the underlying engine to do those kind of queries on the fly. And then all queries must be fast. I think for BI, for Apache Superset specifically, one of the challenges that the people that maintains the data infrastructure, the engine, are not the same group of people that are building dashboards, trying to extract those business insights. So they see a GUI, right? They're not going to really care about, a lot of them are not going to care about, how complex that query is, how many terabytes of data that query is actually scanning, right? Or, just how expensive the whole thing actually is. They all want fast query performance. So for those like edge cases, we need a method to accelerate those queries, on demand, to fix those slow queries or those very expensive, kind of like outlier queries, right? So that is another requirement as well. And so Apache Superset queries, right? So rendering dashboard. So how do we make Apache Superset queries faster? So first, you need to optimize your underlying data warehouse or your underlying engine, right? According to your use case and your workload, right? Your typical data warehousing kind of like tricks and tools you absolutely want to use, take full advantage of, right? Because they're the actual muscle that are moving the data around, actually executing the query. So partitioning, right? So you partition your data, based on how you're gonna query them so you can push down all of your predicates, right? So you scan a lot less data, right? With sorting, right? Like n to log n, right? It's just faster, right, to do things, and just want to sort on the right columns. And also you want to build the right indexes for your use cases, such as you want to do let's say a massive count distinct, right? You want to probably build a bitmap index that's going to help with your query, right? And of course, pre-computation, we're going to talk a lot about materialized views in this webinar. Build those and to alleviate some of the pressures, to do less computation on the fly, right? And also you want to know about how a query is executed under the hood, right? Specifically, for join, how does your query engine also know your query engine really well, right? How do your query engine handle join, right? With some set of specific query, do you want to, depends on the amount of data you're scanning, right? Do you want to still do shuffling, right? Is it shuffleable? Is it small enough so you can shuffle? Or does your query engine actually support shuffling, right? Or it's just too big, you have to do some kind of like a co-located join, right? You actually have to know your query engine really well and to know how a query is executed, and to estimate the cost yourself and to deploy appropriate number of instances to actually cover your BI workloads, right? And then you have to like carry your data, metadata. And this is specifically if you're not using a kind of like a managed data warehouse, right? Like a data warehouse, a lot of them, like most of them, or actually all of them, do this process automatically, fully managed. But if you're using like, let's say a query engine plus a data lake solution, right? You want to carry your data. You don't want too many small data files. You want to do compactions correctly. Too many small data files can really harm your data scanning performance. And metadata as well, right? You don't want too big of a metadata, not enough of them to parallel read, or you don't want too small of metadata. So fetching those metadata can be very expensive as well, right? Through compactions and regular metadata maintenance, right? And this is especially important if you're on a kind of like an open data architecture with, let's say, like a query engine or compute engines plus, Apache Iceberg or Hootie or, Hive, right? And then you have to actually understand like how Apache Superset works. So, like how it handles caching and, how often a dashboard is actually refreshed, how often that is. And that has a lot of effect on your performance, right? You have to know those as well, right? And after all, you have to use the right engine that works for a use case, right? If you're looking to run interactive queries and you have Spark, you can configure the hell of it to make it work, but you're probably better off to use something else, right? That's more suitable for a use case, right? Latency can be a metric, and also the type of query that you run can be a metric, right? And also, is it with a lot of joins, or is your aggregation on, a lot of unique values, high cardinality, and also data freshness is also a consideration, right? Do you require like very fresh data, right? So absolutely choose the right engine that works for a use case, right? And we're going to talk about that like right now from the bottom, right? From the very bottom. It's probably a little fundamental. I'll fly through this faster, right? So first is use an engine that is built to run analytical queries, right? If you're using Apache Superset, you're probably, trying to do something that's analytical, right? So you have OLAP, which is online analytical processing, versus OLTP, right? It's online transactional processing, right? They have very different purposes. So OLAP is really built for problem solving, decision support, discovery, reports and dashboards, and those are what we want, right? OLTP are those, that supports essential business operations, right? And the query type that OLAP is good at are those multi-table queries with aggregations, right, to extract insights. And for OLTP are those, simple standardized queries, like a select where, right? And, it's really good at, those fast and inserts and deletes with transactional properties with like massive of concurrent user changing the data at the same time, right? And data volume with OLAP systems are typically large, with all of your historical data, and and sometimes aggregated, pre-aggregated data from very different sources, layers of data like raw and sometimes pre-computed and more pre-computed, and and the data mart for serving, right? And for OLTP, and you typically maintain the most current real-time data, that's very small, compact, and transactional in nature, right? And data update frequency as well. For OLAP is almost like batch, hours or even days of freshness to near real time, right? Around like the best industry can do is around like 10 seconds, sub 10-second data freshness. So that interval of data updates. But for OLTP system, is much more frequent on the record level, right? And for those, and one of the best way to spot, which system you're using is how storage is oriented, right? OLAP systems tend to use columnar storage. We're going to talk about why and how and more in the next slide. Columnar or hybrid, right? With a columnar and row store, like an HTAP system, or at least with a columnar index, right? And OLTP is mostly row oriented. So columnar storage is, why do we use columnar storage for analytical queries, right? Just imagine a very simple, like how many webinar attendees today are wearing a polo shirt, something like that, right? You're scanning data by the column, right? You're fetching the data in big batches, right? It's essentially a batch operation, right? If you're reading by the column, why don't we store them as column, right? So they're way less disk read, right? You touch disk much less times, right? If you store the same way as how you would access the data, right? So storing column is way faster, fetching data for OLAP kind of workloads. And also columnar storage, because like each column, the data is similar, right? So you get much better compression ratio with columnar store versus row store. It's great for OLAP, typically with massive amount of data, right? And columnar store is basically, okay, you store your data in a columnar format, in columnar batch format, and vectorized operators or vectorized processing. It's basically in memory. We do them by column. We do them by batch, right? And the more batch you go for OLAP, the faster it's gonna run, right? And this is a lot more CPU cache friendly, right? And also, this is way easier to incorporate SIMD optimizations, which is probably one of the most important thing you can do with columnar store and vectorized engine and SIMD, right? This is one of the biggest optimization you can do to OLAP performance, right? And then we're going to talk about how SIMD works with the two, right? SIMD is basically single instruction, multiple data. So, which means that you're able to process multiple data points with one single CPU instruction, right? So let's take a look at the example here, right? So, without SIMD, you would have to touch memory many times, right? Every time you see a value here, right? So this is a multiplication between two vectors, right? So, but you're doing one by one, right? But with SIMD, right, you can SIMD read this whole vector once, and then do the computation once with one CPU cycle. And this is really good for performance, right? Because memory is slow when compared to CPU. And we in StarRocks, we actually did this with CMD and a vectorization, right? This whole thing, operator by operator on a standardized test, we see around like 3 to 20 times performance gain, right? Operator by operator. And in real life, in real life scenario, it's probably even more, right? So if you are trying to do interactive OLAP, you want the best possible performance. Definitely look for something that has CMD optimization. And the best way to incorporate CMD is to write the whole thing in a lower level language like C++, right? So this basically, you want to find something that is columnar store and says they're fully vectorized and it's written in C++, right? And so this is the highest level of of how some high level optimizations and just overall performance, right? One of the biggest effect on performance. And then we're actually going to talk about computer architecture, because there are different type of engines in OLAP that are good at very different things, right? Some of them are more suitable for like low latency, simpler queries. Some of them are like complex queries that runs for hours, and some of them are like complex queries, but you want to run them in second level, right? So first is scatter gather. So scatter gather is basically you have a bigger node and you spread the task into the smaller nodes, right? And it does not really have the ability to reshuffle the data based on the key once the query is already running, right? Based on one query. So, it's a very simple architecture that's pretty robust, right? But it's really easily to bottleneck on one node. Let's say for join, right? Without the ability to shuffle. The best you can do, distributed join is a broadcast join, right? That is, just broadcasting the small table to every single node. And it's very easy to bottleneck on that, right? So it's not really suitable. It's fast if the use case is right. Basically means you have a aggregation that doesn't require like two-phase aggregate. So not like a low cardinality aggregation can run really fast, but it's not that suitable for joins at scale. Basically means bigger tables joined together and with huge data that doesn't fit in one node. And it's not really that suitable for high cardinality aggregations at scale, right? An example of this is like ClickHouse and Druid, right? And then you have those, stage by stage kind of map reduce computer architecture, right? It's able to do data shuffling, right? But for every data shuffle, you persist the intermediate results to disk. This is to not purposely slow down performance, but this is to be more optimized for long running ETL kind of workloads, right? That runs for hours or even days, right? They're wait time between tasks, so they're slower and less efficient by nature, right? But they're really good for those long-running ETL workloads. Something like Spark, right? Is one of the example. And MPP architecture, massively parallel processing. The heart of it is data shuffling, but between nodes memory data shuffling, right? And that enables scalability and performance, right? So it's able to one node process a little bit of the task and send that data to the another node, right? So it's pipeline execution with absolutely zero wait time because we don't touch disk. With this kind of architecture, we don't touch disk, right? So it's able to run everything within memory. So, for those sub-second or second level interactive, joins and complicated multi-stage aggregated queries at scale, this is the architecture that is really great. And I think this particularly is, for most people, is probably the best kind of architecture if you're trying to run BI. Some of the examples can be Trino, Impala, StarRocks, right? There are MPP. And we talked about, query execution, optimization on that front, and how, computer architecture, right? And the next is query planning, right? it's, running queries like, going from point A to point B, and the search space is absolutely enormous, especially, if you support distributed join, right? You can have you have different, like, many tables that join together, right? Like the order of the join, it's make a big difference. And also you have the join algorithm, basically means how a join is executed on each one of the instances, right? You want to do a hash join or a nested loop join, that's join algorithm. And you have this distributed join strategies, right? You want to do a broadcast join, or you want to do a shuffle join. You want to do, those kind of, distributed join strategies, and also aggregation methods, how to configure, runtime filters, right? And even we're going to talk about the materialized view rewrite and many things, to think about, and many ways to execute a query. And the difference between an optimized plan and an unoptimized can be just many orders of magnitude big, right? So this query planning, you want the best possible optimizer if you have joins and aggregations in your workload, right? So you want something that's cost-based. So which means that it's going to collect statistic based on the actual data that you have, right? Periodically, it's configurable. It starts like 10 minutes per by default, and then estimate the cost of each potential plan, a candidate plan, and select the best one, right? And this is today, it's the cost-based optimizer massively outperform rule-based optimizer, especially for complex OLAP queries, right? And this is not that difficult, not that easy to build, and because the whole optimizer is deeply integrated and with the execution and storage layer, right? So they have to, every single cost-based optimizer is almost, specifically built for one system, right? So you definitely, if you have joins and a lot of like high cardinality aggregations, definitely find something that has a cost-based optimizer. Okay, and here are kind of the highest level recommendations. How to pick an engine for Apache Superset, right? It probably looks like a data warehouse, right? Yeah, it is. It does. It does look like a proprietary data warehouse, and a lot of our users before, they were using a proprietary data warehouse for Superset use cases, right? To power Apache Superset. But do we actually need a proprietary data warehouse to do this? The answer I'll use data to talk about in later slides. But take a step back here and think about like what kind of what are the data sources for a lot of the superset use cases. For the user I talk to, a lot of them, the data is already in the data lake, right? It's internal facing. The data freshness is not that big of a ask, right? So a lot of them are actually fetching data from your data lake, right? They're fetching data from their data lake, copying the data into a proprietary data warehouse, and use that data warehouse to serve their Apache Superset dashboards, right? But this does, solve the performance challenges, but it comes with a lot of costs, right? So first, you have to consider the cost of actually maintaining infrastructure level software like a data warehouse. It stores data, right? So it's stateful, very expensive to maintain. And also you have to consider the cost of, the actual ingestion pipeline, right? Writing your data originally in your data lake, probably in the Parquet file, in the open file format, write that into the proprietary file format that is enforced by the data warehouse, right? Rewriting all of your data. And that's a very expensive and error-prone process, right? Data ingestion pipelines, right? And also you have to, move the data. You move the schema too, right? You have to match the schema. You have to somehow match the data type, right? You have to match the SQL. And, that is a very labor-intensive thing to do as well, right? And also you break the single source of truth on your data lake, right? You used to have one copy of the data on your data lake, and that's great for data governance. But once you start copying things out, you have data scattered around in 15 different systems, and data governance becomes an absolute nightmare, when you start doing that, right? So what if we can just run everything on a data lake? But why aren't people doing that, right? data lake queries are actually a little different than data warehouse queries, right? Query engines that are used for data lakehouse today are actually not built for data warehouse like workloads, right? Some of them are optimized for long running batch workloads, like Spark, right? Not really low latency, high concurrency, right? Like to power superset dashboards, right? Or they're built for connectivity, right? To connect to a million different data sources, right? Great connectors, but really not optimized for performance for a few data sources, right? And also on the technical side, data lakes are a little different, right? It's all external storage, so the network I/O is expensive, right? You have to actually fetch the data from external storage to your query, and that's expensive as well, right? And also, you have the slow and unpredictable performance of data lake systems, typically run on HDFS, which is um, just varies the performance, but or some kind of like cloud object storage, like AWS S3, where the response time can be upward of 100 milliseconds, right? And also with data lake, or even data lake houses, like Apache Iceberg, the data files and metadata files are not really that strictly optimized when compared to a data warehouse. Those can be unoptimized for query performance. And so if this sounds interesting to you, to run your kind of BI kind of workload directly on your lake, you want to find a creation that can do, like these things I'm going to talk about, right? So first, the hierarchical caching framework, to kind of overcome the unstable performance of data lake systems, right? To save I/O costs from actually fetching the data from the external storage. So a well-designed caching framework is absolutely necessary, right? And also you want to find something that is MPP, in-memory data shuffling, we talked about in the computer architecture slides, right? And this is to be optimized for low latency instead of batch workloads, right? And also you want to find something that is absolutely built for performance, right? In a lower level language like C++ to fully utilize, SIMD instruction sets to fully take advantage of its performance, right? And actually, with the right tools, getting this kind of data warehouse like performance on the lake or on the lake house is not only possible, it's quite easy to do, right? I'll show an example here. So here we're going to use StarRocks as an example. StarRocks is an open source query engine and data warehouse that excels at both, right? So this StarRocks can be deployed as a data warehouse. So has its own file format and its own table format, right? When deployed as a data warehouse, it can do real-time analytics. Basically, you can ingest data and do data upserts every like 10 seconds and without impacting query performance, right? With its own storage engine. Or it can just ditch its own storage engine and hook a data lake, as its data source. And directly query the data that is managed by, let's say, Delta Lake, Iceberg, Hudi, Hive, right? That sits on top of HDFS or object storage, right? And get great performance. And we can compare the two, right? And first, let's see the performance of StarRocks, as a data warehouse, right? StarRocks is an incredibly fast data warehouse. This is just to set a baseline, right? So this is the SSB benchmark test. Actually, I'll use this for the demo as well, but a terabyte for the demo. So everything on the right, see with a flat, is a denormalized version of this SSB test. It used to be like the original test is multi-table, right? You run on-the-fly joins, but the folks at ClickHouse create an alternative test that only runs the on-the-fly aggregations, but not on-the-fly joins, right? You see, all of the single table test, StarRocks is the fastest, and StarRocks multi-table test is actually faster than Druid's single table and almost as fast as ClickHouse single table. Given that join is probably one of the most expensive thing you can write with a SQL, StarRocks absolutely is optimized for performance. It's one of the fastest, as a data warehouse. And let's see the performance difference between StarRocks as a data warehouse versus StarRocks as a lakehouse query engine, right? So this is TBCDS, is a lot more complex, those like ad hoc queries that a data scientist would probably write, with a lot of joins, a lot of high cardinality aggregations. So the difference between StarRocks using its own storage in its own proprietary format is only 12% faster than it's sitting on top of Apache Iceberg. For this case, Hive, sorry, sitting on top of Hive, right, with Parquet files. And this says a lot, right? By only sacrificing like 12% of the storage, we don't have to maintain another data warehouse. We don't have to maintain we don't have to like copy your data from your data lake. It really simplifies your architecture, like what, Apache Superset does, right? And just a bonus benchmark here, StarRocks is purposely built for data warehouse like workloads. It's around like 4.6 times faster than Trino on TPCD as 1 terabyte, right? So this can absolutely handle the kind of workload, interactive kind of workload, like Apache Superset normally does, right? But without all of the hassle, without all of the overhead of actually maintaining a proprietary data warehouse. Okay, so this is fast query, right? But remember we talked about there's some queries we just have to solve, right? We just have to fix those very expensive or sometimes even poorly constructed dashboards. But we do want them to run fast. We want good user experience for Apache Superset users, right? So we need to find a way to accelerate queries on demand, right? And we normally do them by configuring ETL workloads, pre-computations, right? Let's just imagine, right, with a legacy data stack, how would you do that, right? Let's just say you're a data engineer, right, and your one of your dashboard is running slow, and you identify slow query, and you, after some examination, the only way of solving that is to add a pre-computation to your pipeline, right? Probably in this case, many tables, right? Denormalize many tables, multiple tables into one big flat table, and get rid of the on-the-fly join, which totally makes sense, right? But you're probably gonna do that with something like Spark, right? But it's not the end of it, right? It's not gonna take effect until you rewrite the SQLs to point to the new table. In a BI setting, is to reconfigure the dashboards, right? So you have to bug your user in order for the dashboard to run faster, right? And this process, this rewriting SQL or bugging the user, this process is so frustrating that it forces the engineers to figure out all of the data pipelines, often forces the data engineers to figure out all of the data pipelines prior to like actually developing the client-side application, aka this is the dashboards, right? So when they plan a little more, right? And they end up building pipelines to generate tables that rarely get used or never get used, right? A lot of wasted resource. And most importantly, this really lengthened the process of their POC phase, and they end up going to production a lot slower, right? I think one of the reasons why this is happening is query engines as a whole are running so much faster than before now, right? ETL pipelines are now being demanded to build on demand, instead of like default everything to denormalization or everything to pre-aggregation, right? So it's basically a shift from pre-computing everything to on-demand pre-computation, and this on-demand is a problem we have to solve like today, right? And the way to solve this for us is Materialized view, right? Materialized view is a concept that's been around for a very long time, right? And StarRocks Materialized view, for that fundamental, is nothing really that special, right? It supports multiple table, and it can guarantee correctness of the result, right? And multiple table and refreshes, and it supports SPJG queries, so select, projection, join, and group by queries. But the thing is, the most important thing for StarRocks Materialized view is able to do full query rewrite, which basically means when you have the Materialized view constructed, right, and you have a new query that comes in, StarRocks cost-based optimizer can actually intelligently route that new query to the most appropriate Materialized view. So, you don't have to do the whole computation, right, to save the cost. And you don't have to rewrite the query manually. So you don't have to, rewrite the query to benefit from the materialized view, right? So this by itself, enables on-demand query acceleration, right? So you can just build your data model raw and then spot those slow queries and add materialized views afterward on demand to fix those slow queries, right? Without actually changing your SQL script or bugging your users, right? This is a way better experience for your data users, and it saves compute storage costs from all of those unnecessary pre-computation pipelines you would have built, without this, which is Spark, right? And you go to production way faster, right? And there are a lot more to the rewrite, and this is majority what we're going to show in the demo. But I want to talk about some like little details that are fun, right? I want to share. So first, the rewrite supports select, projection, join, group by, right? That's not all of the queries that are out there, like window functions, right? It's not supported. So, and that's very difficult to implement, with a native query rewrite. But we do have a view-based rewrite that's able to enable query rewrite on nearly all of your queries, right? So instead of writing your queries like queries, just plain queries, you want to encapsulate them inside of views. And then if you want to accelerate this piece of query, you just turn that view into a materialized view. So you just create that materialized view on top of that view, right? And that bypasses all of the SPJG constraint, right? So enable materialized view rewrite for nearly all queries, right? Nearly all means that deterministic functions, right? If you have a current time, it doesn't work. But other than that, everything works, okay? And we also have many detailed optimizations to ensure, the best performance and the best user experience. Something that, you're probably not gonna feel, when you're using it, but it enables many query rewrite that not really possible. Like for this, it's a join on aggregation query, right? And our cosmetics optimizer can actually rewrite this query to extract this this part, right? And this aggregated part, and use the materialized view to accelerate this part by itself, right? So a lot more use cases can be accelerated because a lot of the detailed optimizations we did, and most of them are documented on the StarRocks documentation site, and I'm going to show them later. Okay, and now we're going to do a demo that is based on preset and CelerData. Okay, so we're going to have preset that is powered by Apache Superset as a BI layer, and CelerData as a compute layer, right? That's powered by StarRocks. And then we're going to have data that is stored in Parquet files on top of AWS S3 and managed by Hive tables, right? And we're going to use two data sets because why not, right? We're on the lake. We don't have to ingest. We can use as many as we want. We can use 15 if I want to. And the two data sets, one, we're going to show just a native query rewrite and, how does that affect accelerate dashboard performance. And another one, we're going to showcase a view-based rewrite with a very complex, dirty looking query, right? And how view can help you, kind of accelerate all kinds of queries without any constraint, right? So basically how to accelerate dashboards on demand. Now let's go to the demo. Let me share. Just one sec. Let me find the right window. Okay, my class is still running. That's good. Okay, you should be able to see my screen. Let me see. Yeah, okay. So now we're in the CelerData Cloud BYOC environment. So this is the BYOC version of CelerData. BYOC means bring your own cloud. So, you bring your own AWS account, and this is basically deploying your CelerData on your AWS account, and we kind of manage it from our AWS account. So you own all of the infrastructure and you own all of the data, right? And this is CelerData, and this is preset, right? I've already configured two data sources here that we're going to use here. So CelerData Glue catalog, it's just a name. It's CelerData's external catalog for Glue, right? So we're going to query the data that's stored in an external data lake that's managed by a Glue metastore directly, right? And also we have a CelerData internal catalog. That is all of the data that's ingested into CelerData. But here we only do this because we want to query a CelerData view, right? Because we're doing a view-based rewrite demonstration, okay? And also I've configured a few dashboards, charts. They probably don't look that good, but gets the job done. And now let's go into the cluster and see what we're doing here. Okay, so I've actually already configured all of the materialized views beforehand because we do have pretty big data sets. For the first one, demonstrate raw query rewrite is 100 gigabytes of TPCH, right? It's query number 5. And the materialized view I really constructed here is 600 million rows. So how we're going to go with this is we're going to use this configuration, right? To turn to true and to false, right? False meaning we don't do rewrite, just pretend we don't have the materialized view and switch that back to true. So we have the materialized view, right? Let's first give this a false. So now we don't have the materialized view, right? And then let's run some queries, right? So this is going to be very slow. So I'm going to run this TPCH number 5 first, right? So when it's running, let's take a look at what the query looks like. Okay, so it's a really expensive query, but simple looking. That's why I like that. So it's a join between 6 tables, with the biggest table that exists in the TPCH benchmark test, right? A 6-table join and a easy aggregation, right? So let's see if that is okay. So it's refreshed. Let's go to the query history and take a look at the profile. Let's see what it did, right? So it ran for nearly 12 seconds, which is not particularly slow for the 3 B nodes we have. So in total, that's 16 core each, so 48 cores, right? To run a 6-table join, it took 12 seconds, right? So what if it's too slow? You want to make it faster. You create a materialized view, right? So here, the materialized view we created is here. Okay, it's scary looking, I know, but most of them is just foreign key constraints because we're trying to create a materialized view directly on top of a data lake, right? We need to give it some of that. And the materialized view we did is basically just this, just a denormalization of all of the TPCH tables, right? It's just a denormalization between all of the tables and nothing really special. And here is the key mapping, right? And the materialized view is already constructed is here, right? And now we switch this configuration to true. And we do this, and it's done. Okay, I did it twice. And yeah, it runs so much faster. And let's take a look at why. Okay, so this is the original one. I forgot to show the actual query that's sent from Superset, from preset. So basically, in preset, I constructed a virtual table, which is just a view of all of the of the 6-table denormalized, right? It's a view. And then I configured all of the predicates and group bys, in the GUI, right? And this is almost 12 seconds. And remember what this looks like. And now let's take a look at this. This is the exact same query that got sent from preset, right? But it ran for only 126 seconds, whereas this run for almost 12 seconds. And let's take a look at their query profile side by side. Okay, so this is the 12-second one, the first one without materialized view. So this is pretty nasty looking, right? Because 6-table join, we're able to run it under 12 seconds because we got the drawing ordering pretty well, right? But it's still a very expensive query. But here you take a look at the query profile. Instead of actually running all of the drawings on the fly, it just hit the materialized view, the denormalized Y table materialized view, and only run the way cheaper aggregations on the fly. And that's why the query performance difference is like 100 times. Okay, so this is the first I want to show, just a vanilla rewrite of query number 5 from the TPC-DA, TPC-H benchmark test. And remember, we do have a SPJG select projection join group by. Those are the things that we can do rewrites on, right? But there are other type of queries that are out there we cannot rewrite on. For example, a window function, right? So here I have another SQL that's from the that is based on the SSB data set. It's just a SQL that has a window function. It's really complex, very expensive query. And we just run that for now because, oh, okay, so I forgot to turn that to false. Kind of spoil it there. Do a refresh. Okay, so it's gonna take a pretty long time. So now let's first take a look at the query, right? So it's a query on top of SSB 1 terabyte. So this part, query rewrite cannot rewrite this. And also it has a window function that we cannot rewrite. And this is just inherently just a very expensive query because it's based on the 1 terabyte data set without any predicate, right? And the whole thing, if you just write this SQL, it's not gonna rewrite. So let's see, okay, it's finished. Let's take a look at the query history and see what happened. Oh, it still shows running here. Give it a few more seconds. It does take a few more seconds to update. So almost 30 seconds it took to run this query, right? Remember what this looks like? So it's basically select these from the view, right? From the view we created here. So this actually is a view, right? So this is actually a view here, okay? This view is just this query, okay? And it's very slow, right? It ran for almost 30 seconds. And looking at this, it's a very expensive join because we don't have any predicates to push down. It's just all of the data out there. And then we have an aggregation, right? But what we can do is, this is expensive, right? But we can create a materialized view on top of that view. And basically create a materialized view on top of the view, this view, and then this. Okay, so this materialized view is actually already created here. Okay, and then in the configuration, we just flip this to true and do the rewrite and do the query. It's going to do the rewrite. Oh, this is going to take some time to refresh. Okay, I think it's this one. Okay, nice. Yeah, exact same query. 15 milliseconds, because this basically has nothing left, right? The whole thing is rewritten. So take a look at the query profile, just scan, and it's done. And then result, right? So this is how you can accelerate your Apache Superset dashboards without actually bugging your user at all, right? And this is, we believe the way going forward with, with dashboards and with BI, with metric layers, right? So separating the role between your data engineers and your data users, right? When your data engineer tries to fix a slow query, it should never go to the user, right? The user should never have to actually do anything to be able to benefit from that performance. And StarRocks Materialized is the tool that is built to solve this specific problem, right? And if you want to learn more about Materialized view, the Materialized view I just demonstrated is the asynchronous Materialized view in the StarRocks documentation, right? And there are a bunch of nice use cases. You can learn how to do data modeling with Materialized views and query rewrite with Materialized view. And this has all of the cases that you're probably going to need a little more than you need. And go give this a read. And okay, so this is it for the demo. let's go back to the slides. Okay, I have to play the slides. Okay. Oh, wait. Sorry. Okay. So that's the end of it. Accelerate your superset dashboards. So you can sign up CelerData Cloud, BYOC, with cloud.celerData.com and get the 30-day free trial. And also join the Slack channel if you're into this kind of stuff. You want to do OLAP, you want to do it fast, you like Lakehouse, you like real-time analytics, you want to learn more about StarRocks, or you want to learn more about BI, join the Slack channel, join the 3,000 people that talk to each other every day, solving problems together, right? Now I'll take any questions. As far as I remember, capabilities in shared data mode are extremely limited. No synchronous visualized view, no rewrite, etc. Yeah, this was the case when shared data just launched, and one of the biggest initiative that we're doing right now is to match the capability of shared data with shared nothing architecture, right? And a lot of things are already supported, and rewrite, I think it supports from the beginning. Synchronous visualized view, I'm not really sure. I'll have to follow up on that. But our goal is to make shared data for citizen to support all of the things that StarRocks can do with shared data. See that I see your face, but not okay. Last time I evaluated StarRocks for an Iceberg-based lakehouse, I noticed that materialized views don't work once you perform Iceberg partition evolution. Is that supported already? That I actually have to go back and check. I'm not sure. I've seen this somewhere in the roadmap, but I'm not sure. Let me record. Are you in the Slack channel? I'll follow up with you later, if that's okay. Oh, there's some more questions on the Q&A. Let me. Will the recording be shared? Yes, we do have a YouTube channel for CelerData. Yes, they will be shared like 1 or 2 days after, and we're also going to announce in the Slack channel once that's shared. Okay, so any more questions? I'll wait 10 more seconds for any more questions. Okay, I think that's it. That was probably one of the longest webinar we've had. Thank you for sticking around. And see you guys again next time. Thank you. Appreciate that.